Okay, so today we're going to continue our talk about differentiability, our talk about average rate of change, our talk about instantaneous rate of change, and the derivative. So we talked about and started last class period with AROC, an average rate of change. So if you will remember, average rate of change is F of B minus F of A over B minus A. It is the slope between 2 points, okay? So this is slope between 2 points. Now, if we were to draw a line on a graph, we were to pick 2 points on a graph and draw a line connecting them, then what we would be drawing is a secant line, okay? And the slope of that secant line is that AROC, that average rate of change, okay? So that slope of the secant line is average rate of change. So if we look at this first one, here are points here and here. It says the average rate of change of the find the average rate of change of the function f of x equals x squared plus 1 on the interval from -2 to 3. Okay, now remember, when we're given an average rate of change, the numbers that we are given are both x values. So in order to be able to find average rate of change, we need to go out there and find the y values. So f of -2, if I plug into my equation, that would be 4 plus 1 is 5. And f of 3, if I plug into my equation, that would be 9 plus 1, that would be 10. So my average rate of change is going to be f of 3 minus f of -2 over 3 minus -2, which is going to be 10 minus 5 over 5, which is going to be 5 over 5, which is 1. So that is the slope of the secant line, okay? So that average rate of change is the slope of the secant line. It says, then write an equation of the secant line in point slope form. So remember, point slope form of a line is going to be y minus the y number is equal to the slope times x minus the x number. So that's our point slope form. Now, in this case, we have 2 points, so we just have to pick a point. So for this one, I think I am going to pick, I'm going to get a different color. I think I am going to pick my point is going to be -2, 5. My slope I just found is going to be my AROC, which is equal to 1. So my equation of my secant line would be y minus 5 is equal to 1 times x minus a -2, so it would be x plus 2. So that is the equation of that secant line, this guy right there, okay? Now, we also talked about in our last lesson how we needed to know about change at a single moment in time, because that's a lot of what calculus talks about is change at a single moment in time. So how can we do that when we only know a slope formula with 2 points? How do we do that when we want it to be a single point? Well, remember our average rate of change formula is a difference. It's the difference between the y values and the difference between the x values. Well, if we only have one x and one y value, what are we finding the difference on? Okay, so this is where limits come in, and it gives us the ability to squeeze 2 points together. So let's kind of look at what we've got and where the definition of the derivative comes in. All right, so here's our picture. We want to use the difference quotient to set up the average rate of change between the 2 points on the graph. So here's my first point. If this x value is a, then this y value is f of a, right? We would plug in the a value into our function to get our y value. Now on this, h represents the distance between the 2 points. So this guy right here is a plus h. This is our x1, this is our x2. We go a out and then we add h on. So that was why it'd be a plus h. So this y value right here is f of a plus h. Okay? So now if we do our average rate of change, what we would get is f of a plus h, that y value, minus f of a, this y value, all over a plus h minus a. I guess we'll put that in parentheses. Okay, so that would be our average rate of change. Now here's where limits come in, because what we want is for these 2 points to be closer and closer and closer and closer together. Well, as these 2 points get closer together, or let's just say as a plus h moves closer and closer to a, what's happening to the value of h? Well, h is going to 0 because as they get closer, the closer they are, the smaller the distance between them. So here's where limit comes in. We can't find the value if h is exactly 0. So what we're going to do is we are going to set up a limit as h approaches 0. So we're going to see what happens as it approaches 0. And then that's going to give us a clue as to what our slope would be. Now, the difference quotient is what it is. That's f of a plus h minus f of a. Now, I will clean up the bottom. The a's cancel out, and I have just h in the denominator. So that right there is the definition of the derivative, okay? So this, let's see, is the definition of the derivative. Okay, that's how we find slope at a single point. All right, we look at the difference in the y values divided by that distance h, and we let that distance h go to 0. Now, talking about a slope at a single point, slope at a single point leads us to a tangent line, which is a line drawn passing through a point on a function, and it leads us to slope of the tangent line being this word derivative. Now, last class period, we called it IROC. All right, that instantaneous rate of change, that's synonymous with derivative. So we've got secant line, which is through 2 points. Now we have tangent line, which is through 1 point. Okay, so we're going to use this definition of the derivative to try and find the slope at a single point. So it says find the slope of the line tangent to the graph of the function f of x equals x squared plus 1 at x equals 1. So that means we know 1 point is going to be 1, and then if I plug in 1 plus 1 is going to be 2. So that's 1 point on our graph. The other point, I don't know what it's going to be. It's going to be some distance h out there. So it's going to be 1 plus h as our x value. And if we take that x value and plug it into our equation, it would be 1 plus h quantity squared plus 1. So those are the 2 points that we're going to find our difference quotient with. So we're going to do f of 1 plus h, so f of 1 plus h minus f of 1 all over 1 plus h minus 1. And then remember, we want that h value to go to 0. So we're going to look at put our limit in front. Now let's plug in what we have. We're not evaluating our limit yet, so it'll stay there. But we do know that f of 1 plus h is this quantity 1 plus h squared plus 1. So I'm going to FOIL it out. So if I FOIL that out, it's going to be a square double square. So it's 1 plus 2h plus h squared. Then we have a plus 1. So we have all of that minus f of 1, which is 2, all over 1 plus h minus 1. Now, before we can evaluate this, we need to do some cleaning up. So we still have our limit, because I'm still working inside the limit, trying to clean it up. If I look at this guy right here, this is really 1 plus 1 makes 2 plus 2h plus h squared. Then I have a minus 2 back there. And in the denominator, my 1's cancel out, and I have just an h. Now, I'm not quite done cleaning up because I can cancel these 2's out. So then I have the limit as h goes to 0. And I've got h's in common on the numerator, so I'm going to pull an h out. That leaves me with a 2 plus h, and then in the denominator, I have an h, which means I can cancel those out, which leaves me with the limit as h approaches 0 of 2 plus h. Now I can do direct substitution, so that would give me 2. So what we're saying is that if this is our tangent line right here, the slope of that line would be 2, okay? Now, if we want to then write the equation of the tangent line, we're going to write it in point slope form, and I am going to use that as my point, and we just found my slope was 2. So our tangent line is going to be, remember, y minus the y value, so y minus 2, equals the slope, which we just found was 2, times x minus the x value, so that would be x minus 1. So that would be the equation of our tangent line, okay? So we found what the slope is at that single point 1, 2 by algebraically manipulating what we call a difference quotient and evaluating a limit. What is it going to look like as h gets closer and closer to 0? Well, that slope is going to be closer and closer to 2, okay? All right, so talking about notation for derivative, so this is all your notations for derivative. You can talk about f prime of x, okay? That tells you the function name and the independent variable. You can talk about y prime. You can talk about dy dx. You can talk about df dx, and you can talk ddx of f of x. So all of those are proper notations for derivative, okay? This is the formal definition of the derivative. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. We've been doing that. We just had our number plugged in for x. So it's f of 1 plus h minus f of 1 over, and we got down to h after they canceled out. So this is the formula for the definition of the derivative. Okay, so we are going to do this generic formula on our function right here. So our function is f of x equals negative 16x squared plus 96x. So plugging into our formula, we have the limit as h approaches 0. Okay, f of x plus h. Remember, that means we're going to take x plus h and we're going to stick it inside of the equation. So we're going to have negative 16 times x plus h quantity squared plus 96 times x plus h. So that is our f of x plus h. Then we're going to have a minus. Now we want f of x. Well, that's just going to be the original function as it is, negative 16x squared plus 96x. And then all of that is going to be over h. Now, here's where our algebra comes in. We've got to FOIL this guy out. So I think I'm going to write him right above. So x plus h squared is going to be square double square. So x squared plus 2xh plus h squared. And so when I go to rewrite, I'm going to have the limit as h goes to 0. Okay, so negative 16 times x squared would be a negative 16x squared. Negative 16 times 2xh is going to be a minus 32xh. Negative 16 times h squared is a negative 16h squared. And then if I distribute my 96, I would have a plus 96x plus 96h. And then, sorry, if I take my negative and I distribute it over here, I would get a positive 16x squared and a minus negative 96x all over the denominator h. Now that's as bad as it's going to get. Once we get through that, everything should start canceling. So I've got a negative 16x squared and I have a positive 16x squared. So those cancel out. I've got a positive 96x and I've got a minus 96x. So those cancel out. So what you'll notice, what's left over, everything that's left over involves an h. So I am on the numerator. So I am going to factor an h out front. So I'll have the limit as h goes to 0. If I factor an h out front, I have a negative 32x minus 16h plus 96 all over h. Now my h's will cancel and I can do my direct substitution. So if I plug 0 in for h, what I end up with is a negative 32x plus 96. So what you have just done is come up with an equation for the slope at any x value on the graph. So we can take any x value we want and we can plug it into this equation and it will give us the slope at that point. So if I take the x value 0 and I plug it into my slope equation, 0 plus 96 is 96. So what I'm telling you is at this point 0 on the graph, this slope is 96. Oh, you can't see it. This slope right here is 96, 96 over 1, okay? If I take 1 and I plug it in, and you know me, I don't do math very well. So if I do negative 32 plus 96, I get 64. So at 1, wherever it is, here's 1. The slope at that point right there is 64. Now, it may not look like it, but if you look at your y values, that's 50, 100, 150. So my y values are really big. So at 2, it would be a negative 64 plus 96, so it would be 32. At 3, it would be negative 32 times 3 plus 96, so it would be 0. Now, where is 3 on our graph? If we take 3 and we run it all the way up, what do you notice is happening at that point right there? Okay, that's the vertex of the parabola, and it's the place where the parabola changes and switches from increasing to decreasing. So our slope is 0. And then we could do it 4, so negative 32 times 4 plus 96. So that would give us a negative 32 at 5. We would get a negative 64, and at 6, we would get a negative 96. So notice that before 3, our slopes are all positive. Okay, and notice as we are going along our graph, if we were to draw little tangent lines, those slopes would all be positive. Once we pass that vertex, though, notice that all of our slopes are negative. So as we come down the hill, those little tangent lines are all going to be negative. Okay, or the slopes of those tangent lines are all going to be negative. All right, so now we want to write the equation of the line tangent to the graph at x equals 2. So the first thing we need is a point. So I need to know f of 2. So f of 2, I got to plug it back into my original, would be negative 16 times 4, that'd be 2 squared, plus 96 times 2. So I got 128. And from our table up here, our slope is going to be f prime of 2, which according to our table is 32. So then our tangent line is going to be y minus the y value, which was 128, equals our slope, which we said was 32, times x minus the x value, which is 2. And there's our tangent line. So at 2, if I were to follow it up, at this point right here, this tangent line has that equation. Okay. All right, what else have we got? Okay, alternate forms of the derivative. We started out by looking at the derivative at a point. So if we want the slope of the tangent line or we want the derivative at a point or a numeric value for a derivative, then we can use one of these two definitions. So we've got the limit as h goes to 0 of f of a plus h minus f of a over h, or the limit as x goes to a of f of x minus f of a over x minus a. So each of those will provide a value for the derivative. So whereas before we got, where was it? Before we got, here we go, an equation for the derivative, and we could just plug x values in. If we use this derivative, we're going to get a number, and it's going to be specific to the x value that we used to begin with. Okay, so let's look at, let's use this one. So we want to use the alternate form of the derivative to find the slope of the tangent line to the graph of f of x equals 2x squared minus 3x at x equals negative 2. So our f prime of negative 2, that's our x value, is going to be equal to, now for this definition, a is equal to negative 2. So we're going to do the limit as x goes to a, which we said was negative 2. We're going to do f of x. Well, that's just the function. 2x squared minus 3x minus, now we're going to do f of a. Well, f of a is just f of negative 2. So that means we just need to plug in our negative 2 into the equation. So the negative 2 squared would be 4. 4 times 2 would be 8. 8 plus 6 would be 14. And then the denominator, we would have x minus a negative 2, so it'll turn into x plus 2. Okay, so now what we need to do is simplify, because if I do direct substitution right now, what I'm going to get is 0 over 0. And one of the ways that we got around 0 over 0 was by factoring. So we're going to set this equal to the limit as x goes to negative 2. Okay, so we want to factor the numerator. So I'm going to come down here. We've got a 2x squared minus 3x minus 14. So let's see, we need to multiply to negative 28, and we need to add to negative 3. So how about a negative 7 and a positive 4? Yeah. So 2x squared minus 7x plus 4x minus 14. So x times 2x minus 7 plus 2 times 2x minus 7. So that would give me an x plus 2 times 2x minus 7. Okay, so I factored it. So now I'm going to take that factored form on top. So x plus 2 times 2x minus 7. And then the denominator is x plus 2. Lo and behold, I can cancel out my x plus 2's. And so what I'm left with is the limit as x goes to negative 2 of just 2x minus 7. Now I can do direct substitution. So that would be negative 4 minus 7 would be negative 11. So what I'm telling you is that f prime of negative 2 is equal to negative 11. Okay, or the slope of the tangent line to the graph of y equals 2x squared minus 3x at x equals -2 is -11. Okay, so that's what we're telling you. So notice, if we wanted to now go find the slope, let's say at +3, we would have to do this whole process again, because this is only for -2. When we did this formula, we got a generic equation and we could find the slope at any point based on that generic equation. So it's just two ways of doing it. Okay, now the good news is with definition of the derivative is you don't often have to evaluate the definition of the derivative. What you have to do is you have to recognize it as the definition of the derivative. So here are 4 different definitions. Well, actually there's 3, 1, 2, 3. Definition of the derivatives, and we are going to use the definition given, our function given, and we are going to find a limit statement for each of the following. So if we want to find f prime of x and we want to use this definition, here is our function tangent of x. So it is going to be the limit as h goes to 0. Okay, we are going to take x plus h and we're going to plug it in for x. So we would have tangent of x plus h minus, now we're going to write the original function as is, tangent of x, all divided by h. And that's all you need to do. You just need to get practice setting them up. Okay, if we want to find f prime of 3 with this, oh, this one is a C instead of an A, it doesn't matter. So in this case, our C value is equal to 3. And then this is our function value. So for this limit, it's going to be the limit as x approaches our number, which is 3. Then it's going to be f of x, which is the function as is, square root of x plus 2, minus f of c, which is the function with our x value plugged in. So if I plug in 3, I get square root of 5 over x minus our x value, which was 3. Okay, so there would be our setup. Okay, this one is back to the alternate version of the h definition. Here is our x value. So our x value is, our c, let's see, we call it our c. So our c value is -1. Here's our function. So we start out with the limit as h goes to 0. Now we need f of c plus h. Well, remember, our c is -1, so our c plus h is -1 plus h. So that would be the natural log. Then I'm going to put -1 plus h. I'm going to square it because it's x squared. Then I've got my plus 2. So that finishes out the natural log. Minus, now I'm going to plug in -1 into my function. So that would be 1 plus 2 is 3. So that would be the natural log of 3. And then all over h. Okay. Oops, let me get it on there. All right, and then the last one, we're using our c definition. So 2 is our c value. Here's our equation. So it would be the limit as x goes to c, which is 2. All right, f of x is just the equation as is, 1 over x plus 7. Minus f of c is the equation with our 2 value plugged in. So that would be 1/9. All over x minus our c value, which was 2. So that's part of what you're going to have to do on your homework, is just setting up that definition of the derivative, okay? Now, on an AP style test, most of the time what you have to do is do the reverse. You are going to be given the setup, and you have to identify the function and what it's finding, okay? So if this is the formula that we're using, x goes to c. So this right here is our c value. Now on our numerator, this is f of x, this is minus f of c. So if we want our function, it's found right here by sine of x. So f of x is equal to sine of x. What are we finding? Well, we always find a derivative, so it's always going to be f prime. The question is there a number or not? In this case, there is. We have a c value of pi over 2. So we're working backwards. Okay, so here's our limit as h goes to 0. Now, when we have a limit as h goes to 0, this guy tells us nothing. Okay, so we have to identify it by the numerator of the problem. So remember, this is f of x plus h, and this is f of x. So our function, f of x, is going to be 5x minus 3. Now the question is there a numerical value that we're finding the derivative of? Because this guy is an x, then there is no number and we're just finding f prime of x. Okay, now let me show you one where there is an x. So again, the limit as h goes to 0 tells us nothing. So this right here is going to be f of x plus h, and this right here is going to be f of x. Now here's where things kind of go strange, because f of x is not 3. So you've got to remember that this is f of c. Okay, so some number has been plugged in. So if we look at this guy right here, that is going to tell us our function. So our function is the square root. Now I'm going to replace 9 plus h with just an x. So that's our function. And then we're finding the derivative f prime. And since it's x plus h, our x value is 9. And the square root of 9 is 3, which is why we have that 3 out there. Okay, those are the hard ones. So let's do another one. So again, limit as h goes to 0 doesn't help us any. So this guy right here is f of c plus h. This guy right here is f of c. Okay, so we need to work here. I should have something with the h. So what number can I add to h and not change its value? Well, that would be 0. So this guy right here can be rewritten as e to the 0 plus h. That's the only thing I can add and not change the value on that. So my function, we're going to replace the 0 plus h with just an x. We're going to go back in time. It used to just be an x. Now, our c value, we're finding the derivative. Our c value is the number that's in front of the h, which is 0. And then remember, e to the 0 power is 1, so that's why we get the 1 right there. Okay. All right, now, again, we don't do a whole lot with definition of the derivative. You're mainly having to work your way backwards through it, okay? But question types and what you could get, if you're given one point, you can find an instantaneous rate of change. You can find the slope of the secant line. You can find the derivative. You can use the definition of the derivative. All of those are synonymous with the same thing. If you're given 2 points, then you can find your average rate of change. You can find your slope of the secant line, and here's your AROC, okay? Notice that the limit is missing when you're at 2 points, and you only have the limit when you're at a single point. Okay, now we'll learn rules to be able to find derivatives, so we'll get off of the definition of the derivative next class period. All right, if you have any questions, come see us, guys. Thanks, bye-bye.